All right. So until the last class or last few classes, what we have studied? We have studied about queuing. Okay, queuing at input ports, queuing at output ports. Okay, and we have also seen an analysis with a bufferless queue. All right, and finally in the last class we have seen an analysis with the input ports. I mean, with a scenario where you have buffers at input ports. Acha, these rough works which I am doing on this whiteboard, so these I will not share, of course, because I do not save these things. These are rough works, so please take notes of these when you are attending the class. All right, I will share the PPTs with all of you. Okay, so we have considered in the last class that how we can analyze a scenario where you have a single server based queue and you have buffers at the input ports. Okay, and we had also talked about different variations like MG1, MD1, MMM, and MM1B, and also M. These are the variations that we have studied using queuing theory. Okay. Now, what did we find out? We have found out that if we have buffers at input ports, then the theoretical maximum switch utilization that you are going to get is about 58.6%. Okay. So, what are we seeing? That even if we are doing our best with buffers, we are getting lower switch utilization. Now, I had asked you a question in the last class as to why is this happening? Because if you have a bufferless switch, then you are having, I think, around 63% utilization. Whereas if you are having buffers at the input ports, you are having 58.6% utilization. So can someone tell me, has any one of you thought that why is this happening? Because I had asked this question and I had told that I would like to hear this reasoning from all of you. So can any one of you think of why this is happening?
Ma'am, is it possible that if we do not have input port buffering, when there's contention at the output port, one of the packets is simply dropped, whereas if you have input port buffering, we do not drop, which may lead to more contention down the road, and head of line blocking, which which decreases the utilization.
Yes, Acha, somebody else also wanted to say something?
Ma'am, even if you have buffers at input port, same thing only. There could be there's a possibility of the blocking at the input port, even if the output port is free.
Yes, yes, that is true. So that is the reason basically that why we are having a lower switch utilization in case of buffers at the input ports rather than for a bufferless switch. Okay. So what we need to do, we need to improve. We need to improve. How do I say this? Input queuing. Okay, I'll call this as input queuing or input port queuing. Okay, so whenever I'm saying input queuing, it will mean that we have queues at the input ports or buffers at the input ports. Okay, so we need to improve this entire efficiency that we are getting with input queuing. Okay, because yes, if one can say that yes, let us just have then bufferless switch. Why are we even talking about having buffers at the input port queues? Okay, because having buffers does help us in the long run. Having buffers will help us to not lose many important packets. Okay, if in case of bufferless switch, you just can send one packet at a time over the ports. If too many packets are coming at the same time, or if there is a lot of bursty traffic coming, then you are basically going to lose out a lot of packets at the same time. Whereas when it comes to having some buffers at the ports, you can keep those packets until they can be scheduled, depending upon how you want to schedule the packets over the switch. Okay, so we do have some advantages of buffers. So we want to use the advantages of buffers, and we want to increase the efficiency of the system also. Okay, so what are all the different ways in which we can help in improving the efficiency? Okay, or some techniques to improve input queue switches. Okay, so what can we do? Okay, now we can say that let us have buffers. Let us consider these as buffers. Let us suppose that one packet that wants to go to output port 1, here it wants to go to output port 2. Okay, so these are input port buffers. Okay, so these are all input ports. I'm not drawing the entire switch. Okay, and these are buffers. Okay, so one way is that, instead of looking at the entire queue of the input port, you simply have one module that acts as a scheduler for these packets that are basically arriving at the input ports. Okay, so what you do, you check some L number of packets or Li number of packets, okay, in each port. So suppose I say that let it be just L. Suppose I say that L is equal to 2. Okay, that means I'm going to check only first two entries in each of the buffers. Okay, so like here I am seeing that 1 and 2 packets are destined for port number 1 and 2 for input port 1. For 2 input port 2 packets are destined for 1 and 3. For number 3 packets are destined for 3 and 4, and for 4 packets are destined, both packets are destined for port numbers, output port numbers 2. Okay, so what is the best that you can do in this scenario? Okay, so here you see both are destined for output port 2, so you just give this guy the access. Okay, now what we are doing, we are having a scheduler where packets, it is not like the first one who's at the head of the line will be transferred. Okay, so out of these two, anyone can be transferred because anyone can be transferred depending upon which one is causing least amount of contention throughout. Okay, so here you choose this guy, packet number 2. Okay, here you have 3, here you have 3, so that means there can be a contention. So 4 is not having contention anywhere, so you choose 4 here. Okay, then again in this one you can choose 3 here. Okay, and for this one you can choose 1. So this is a good scenario here. And if you have like 4 output buffers only, so therefore 4 output ports only, then you have like 1, 3, 4 and 2. All of them are getting utilized and you are getting around 100% utilization. Right, is this clear what I'm trying to say? Please give a yes or no answer.
Yes, ma'am.
Okay, so this is a very simplistic scenario. Okay, now there can be other scenarios for this also. This is a very good scenario. You had like 100% switch utilization. Now let us get to another example. So you have like 1 here and 2 here. Again, in output port 2, input port 2, you have 2 here, 1 here. Then you have 4 and 3, and then you have 2 and 2. Now, can we get 100% utilization in this scenario? Can we get a scenario where we can send packets to correspondingly output port numbers 1, 2, 3, and 4 at the same time instant? Can we do this?
No, ma'am.
No, because we will have a contention, right? We are going to have contention. So 100% utilization is not going to be possible. Okay, the utilization will be less than 100% here. Okay, so this is not possible. So also, what are the problems here? Okay, so I'm just going to write disadvantages. Advantage is that you can get, sometimes you can get 100% utilization. Okay, and given the structure that you are already having, you can just see that, okay, fine, let us check few L's, and out of that you can check that, okay, which ones should we send. But what are the challenges that you will have? Or maybe I can write as challenges here. First is what? Yes,
ma'am, one question can I raise? In the
yes.
previous example, is it mandatory that only one should be picked up from a buffer, or if it's possible, we can dispatch two numbers also?
No, we are sending one at a time. It is not a batch sending. Yeah.
Only one should be picked up from a buffer.
Yes. One
Okay.
packet.
Okay.
All right, what was I saying? Yeah, so we have disadvantages, and we are going to see that what are the challenges that we are going to face. So what should be the value of L? Okay, if it is too small, then you are basically losing out on, there could have been some scenarios where, like, you are having like 4 and 3 and like that, and you can, like, suppose in this case, let me just suppose in this case, if L is greater than 2, some value like 3 or 4, maybe you could check that, okay, this is probably asking for 3, this is probably asking for 4, this is probably asking for 1, this is again probably asking for 3. Like that, you can just check that, okay, whether I can do a better job or not. So if L is too big, then you have to basically go ahead and check for a really long time. That is going to cost you time. Okay, whereas if L is too small, it might cost you contention. Okay, it might lead you to contention. So value of L is important here. Okay, so that is one problem. Then what do you have? Earlier things were easy. You were simply doing like FCFS, whatever was entering, you were just leading it out to the switch. Okay, if we were having head of line blocking, then okay, fine, there will be a contention, they will wait, and then again, once it is sent, they will be sent. But the scheduling was not a problem, but now you have to schedule. Okay, so things become a little bit more complex than they were. Okay, so every time, so what is the basic problem here? That you are having complex buffer management. Okay, so this is one disadvantage. Then you can have 100% utilization, but not always. Okay, so this is a very simple scenario. And how many and what is the, you are basically considering order of NL packets at a time for, to find out that what is the basic schedule. Okay, depending upon L's value, your complexity will change. Okay, so this is the issue that you are basically, these are the features that you have, and these are some challenges that you are going to have. Okay, when you're using this kind of a improvement or enhancement in input queuing or input input port buffering. Okay. So in order to improve this, we had seen in the last class that can we do something better, and then I spoke about the concept which is known as VOQ or virtual output queuing. Okay, so today we are going to study a little bit on virtual output queuing. So let me just give you let me just give you a brief introduction on this thing. Start. So all right. So earlier what we were having that in one input port we are getting packets which can be destined to any output port. Okay, 1, 2, 3, 4 like that. Okay, but for that what was happening that you have to choose an L value, and depending on that you can check that okay, which of these packets are we going to consider, and whether the value of L is small or big, that will result into whether there will be a higher amount of contention or a lower amount of contention, and it will also lead to higher complexity. That's what we have seen. Okay, so the improvement that was basically the improvement that was enforced, or the improvement that was suggested, yes, the improvement that was suggested is that why not we have, like, why not think of as each input port having different buffers. Okay, so now you are not having a single buffer. Okay, you are assuming that in your port you are having buffers which basically represent different output ports. Okay, became too small. Let me just, so yeah. So this is your input port. Okay, and these are buffers which are representing different output ports. So suppose this represents output port 1, 2, 3, 4. This is for input port number 1. Okay, so that means if there is, so this is the arrival. If there is a packet that arrives that intends to go to output port 1, so this will go here. If there is a packet that intends to go to output port 2 but is arriving at input port 1, then you put it here. If there is a packet that intends to go to output port 3 but it is arriving at input port 1, so you put it here, and then so on and so forth. Okay, so if at all there is a scenario that in your input port 1 you have like so many packets which are arriving for input port 2, but only few packets that are arriving for the other output ports. Okay, so that means the contention is for output port 2, and you can actually send these packets whenever you have the chance to send. Okay, whenever the output corresponding output ports are free, you can actually send these packets, leading to a much lower amount of contention. Okay, so this is basically our concept of virtual output queuing. So if I have like n output ports, like n input and output ports. Okay, so basically what you are going to consider you have n input ports and for each one of them you will have n output port buffers, right? So order of n cross n packets are to be considered for scheduling. Okay, so these number of packets we are basically going to consider for finding out that what is the best way in which you can avoid contention and send these packets. Okay, so in this case also we can see that you can actually think of scenarios where 100% utilization will be possible. Okay, but again in cases, okay, so not always. Okay, and what is the other problem that we are going to have similar to the previous one? Because see, again one scheduler has to schedule these now, it has to check that okay which one is free, what about the other ones, what about the other input ports and their corresponding virtual output queues. So depending upon all of these inputs, the decision has to be taken every time that from which input port which packet will be sent. Okay, so for this case also we will have the issue of complex buffer management. Okay, so clear this part? So I will start with fully like I will dive deeper into this virtual output queuing. Today I'm just going to give you brief ideas about different variations that were proposed for enhancing the switch utilization of input port queuing or input queuing. So now let us come to another scenario where you have, so this is another scenario, let me give number 3. So here what we have combined input output queuing. Okay, so this is the switch that we have always been looked up, that is you have buffers at the input ports and you have buffers at the output ports. Okay, so 1 2 and 1 2. Now let us assume that this is the switch is k times fast. Okay. So why we are going to consider this scenario? Because see, if we are considering a scenario like the question that was raised a few minutes back, that are we sending only one packet at a time? Okay, yes, we can send that time. In the previous time we were sending one packet at a time from the input port because the output port was not having any buffer. Okay, so if for a particular output port you are sending more than one packets together, then those packets will be lost at the output port. But now what we are having, we are having buffers at the output port. Okay, so what we can do, we can send more than one packets at a time, but for that your switch fabric has to be fast enough to send that. Okay, now if you make k n times fast, then also it will be a problem that you are trying to send all the packets together at the same time. Suppose there is like all the other ports are free and you have only one port where all the packets are getting sent towards the same output port. So that means all the n packets are getting towards the output port buffer, and depending upon your buffers size, output port buffer size, its line card speed, then again there will be issue here, okay, at the output ports. So we try to, so in order to, it has been found out that in order to have a better switch efficiency or switch utilization, k can be less than n. So you will have a better utilization if you have the value of k to be less than n. But k should be some, or the switch should be faster, sometimes faster, because with that you can send some k number of packets to the same destination at a time. Okay, this will increase the overall switch utilization. Okay, so these are some variations that we have. Okay, and now one by one we are going to look at the scenarios, or we are going to see that in detail how they all work, and what are the complexities that we are getting. Okay, so for that now I will start the presentation. Okay. Is the presentation visible to everybody?
Yes, ma'am.
Acha. So I'll take just 2 minutes. I just want to drink some water. All right. Hello? Hello, am I audible?
Yes, ma'am.
All right. Okay. So we will start with virtual output queues today. Okay. So let's see what are the key characteristics for designing internet switches and router. Okay. So we need to check for scalability in terms of the line rates that we are getting at the ports. Okay. Then we also need to check that what are the number of ports that your switch can actually support. Switch fabric, that's what we were checking for when we were looking at, you know, the different generations of router we were looking at, and we have done some numericals for the first generation of routers. All right, so we need scalability in terms of number of interfaces that your switch fabric can support. Now, what will be the problems when we are looking at, you know, a scalable switch fabric? The first problem that we get is that when we are having input ports, input port buffers, so then the first problem that we basically see is that you will have the issue of head of line blocking. Okay, that means for if we are using FCFS, so for any packet that is basically standing in front of another packet, which could get a chance to go to the output port queue, but because of contention for the same output port here at the first packets in the queue, they are facing contention. Okay, had it been the scenario that a scheduler is there and the scheduler is basically selecting these packets, whatever the reason of head of line blocking may be, they are not bothering about it, they are simply selecting the packets one by one, so then this issue would not have come. Okay, but for a simplistic scenario it is very difficult. Just think about it, it is very difficult not to have a scheduler, implement it in a hardware scenario, and then work with this. So that becomes pretty difficult. So that is why when we say that we're having complex buffer management for those other scenarios that we just talked about, that is improvement on input queuing. So you know, those are the issues that we are talking about, that if you do this on a, you know, if you program these things, great, it will work out, but if you have to do this on a hardware, then it becomes a little more challenging than what it looks like. Okay, so this is the basic problem that we have, that is head of line blocking for our switch fabrics. Now, this is the scenario that I was basically talking about. So one of the improvements that we just talked about is for virtual output queues. Okay, so this is for virtual output queues. Now, what is the basic feature that we were looking for, that we have seen for virtual output queues? That is, at each input port we have queues intended for different output ports which are present in the switch fabric. Okay, so if you have like n input and n output ports, so at each input port you will have n queues, each one of which is associated with an output port. Okay, what is another feature here? That is, only one packet can go from an input port at a time, and only one packet can be received by an output port at a time. Okay, these are some conditions that you have for virtual output queues. Now, what is one feature that a virtual output port provides? That it retains the scalability of FIFO input queue switches. Okay, that is, we do not have the no memory bandwidth problem. Right. Also, if you have, we just saw this head of line blocking problem, right? So if you use virtual output queues, that problem will not be there, right? So the problem of head of line blocking will be eliminated with FIFO input queues. Now this is how your virtual output queue would look like. So suppose this is a crossbar switch fabric. Okay, you have a crossbar switch fabric and you are having like, these are your output ports correspondingly given in red, blue and green. Okay, and these are your input ports on the left hand side, where you have 3 different buffers corresponding to different output ports. Okay, so now you can see that for input port number 1, okay, for input port number 1 you have packets arriving for output port number 1. Okay, there are no packets which have arrived for output ports 2 and 3. For input port number 2 you have 1 packet each which has arrived for output ports 1, 2 and 3. Okay, and for input port number 3 you have 2 packets that have arrived for output port 1 and 1 packet that has arrived for output port 2. Okay, now the task will be there for the scheduler to schedule the packets. Okay, you are basically scheduling the packets which are here at the head, okay, head of the line of these buffers. Okay, so now you're basically checking more number of packets than what you were checking earlier. Okay, so you just try to find out the best combination for input and output ports. Okay, so that you have the minimum amount of contention. Okay, so what you did, you basically connected this path, that is from output port input port number 3 to output port number 2. So virtual output queue of port number 3 is connected to output port number 2. Okay, so this is in blue, you can see. And then from input port number 2 you have connection to output port number 3. So this is in green, the path you can see. And because input port 1 had packets destined only for output port 1, you are basically connecting the path from input port 1 to output port 1 for sending one of the packets. Okay, so this is how your virtual output queue basically works. All right, I hope that this part is clear now with the visual representation. Now let us see that how packets basically move inside a virtual output queue system. Okay, so see, the green one, the green packets represent packets destined for output port 1. Red packets represent packets destined for output port 2, and the blue packets represent packets destined for output port 3. We have a crossbar fabric, switch fabric here, and this is the scheduler which is responsible for scheduling these packets and then the connection of paths to the corresponding output ports. Okay, so now what are we going to do here? There are packets that have arrived, that is one packet each for input port 1, 2 and 3. For ports 1, 2 and 3, for ports 1 and 2, the packets that have arrived are intended for output port 1, and for port number 3, the packet that has arrived is intended for output port number 3. Alright. Now, what will happen here? You have packets which are waiting here. So both for input port 1 and input port 2, you have packets that have arrived for the same output port. Okay, and there are many more packets which are still waiting in our input port 1, which want to go to input port output port 1. Okay, so what happened here? So packet arrived at input port 2 and it saw that okay, I can actually get connected to output port 1 without contention. So here I can send my packet to the output port 1. Okay, so this is what has happened. So now what we can do, that for this particular time instant, the path can be made from this particular input port to the corresponding output port. Now in the next schedule, what will happen? Let's just assume that this packet is now delivered. Now in the next schedule, what is going to happen? This is what happened. That means in the next schedule, what we did, we connected the input port 1 to the output port 1 because it had a lot of packets to be sent. Okay, then what happened? There were packets that were there in this input port 2 which were destined for output port 2, and there were packets which were which are basically in the output port input port 3 destined for output port 3. Okay, so you can see that and here we had in the previous see here in the previous slide, you have packets, you have one blue packet here in input port 2 and you have one red packet here in the input port 3. Okay, so we can actually connect them in such a way so that they can go to the corresponding output ports here. There's only one packets in these queues left over. So what you do, basically you now send these packets. So the path, you can see that this guy got connected to output port 3, this guy got connected to output port 2, and this guy was anyways connected to output port 1, input port 1 to output port 1. So this is how in the second iteration you basically sent the packets. All right, so basically what is happening in case of the VOQ architecture? All right, so this is your crossbar switch, this is the scheduler. Okay, now what is the task of the scheduler? That at each point of time, that means at each iteration, what is it going to see? It is going to see these packets. Okay, packets at these virtual queues which are present at each of the input ports. Now the task of the scheduler is that you have to, the scheduler has to check that which of these are, how many packets are there for at each one of these buffers. So that means which kind of packet is basically arriving more for a particular input port. Okay, it has to also check that okay, among all of these packets at the heads, okay, which one will face least amount of contention as compared to all the other input ports which are here. Okay, so now it has to check so much at each iteration. Now mind you, once it does that, then after that it has to ensure that the path is available with the crossbar switch to send the packet from the corresponding input port to the corresponding output port, and then the path needs to be established. Okay, so the scheduler's task becomes too much here. At each point of time, it is checking so many packets at the head of line, and then ensuring that whatever path, and then ensuring that the path also exists in the crossbar switch for the corresponding output port, and then it has to ensure that whatever packet it is choosing or whatever path it is trying to establish between the corresponding input and output ports, there is a lot of there is a least amount of contention with that. Okay, so this is the basic complexity that you have when it comes to a scheduler for a VOQ architecture. Okay, so this is what I was trying to tell you, that for a scheduler, the question is that which packets I can send during each configuration of the crossbar. Okay, so that is one question that the scheduler has to answer. So if we look at the basic switch model for a VOQ, how it will look like, there are arrivals that are arriving at each of the input ports. Now once it arrives, then it is getting divided, right, depending upon where it is destined to. Okay, so it is getting divided into the different virtual output queues at each of the input ports. All right, so that means A11N, A1NN. These are the arrivals that are now going to the corresponding queues here. Okay, so the queues are represented as these L11N and then here up to LNNN. So here up to L11N to L1NN, and here up to LN1N to LNNN. So these are the basic arrivals that are happening at the queues, virtual output queues. You have the switch fabric here. So for each input port, now what you have to do, that you have to check all of the inputs which are there in the buffers. Now you're not checking the entire buffer, right? You are checking the first parts of it. Okay, so you are just looking at the lth packet here, and then you are checking that, okay, now with these arrivals or with these inputs that I'm having, where should I match this particular port, input port, to a corresponding output port. Okay, so basically what it looks like, you are basically trying to match an input port to a corresponding output port. Okay, so this is what it will look like, right? So now let us see. So some of the definitions before we go further. So we define a traffic matrix here. Okay, that will be basically representing the arrivals that you have. Okay, so we represent it as, gamma is equal to lambda ij, mod of lambda ij, or just absolute lambda ij. This is, sorry. So where lambda ij is equal to expected value of expected number of arrivals. Okay, that is aijn. Okay, so that is your lambda ij. Now if your total number of arrivals, okay, at the input ports is less than equals to 1, and total number of arrivals at j is less than equals to 1, then we say that the traffic is admissible. Okay, so this is what is defined as the traffic matrix. Then the service matrix is also that, S is equal to Sij, where Sij is equal to 0 or 1, and S is a permutation matrix. Okay, now this is the queue occupancy that we can have. This will depend upon how many arrivals you are having. Okay, this is representing basically that each of these virtual output queues, what are the values of entries or arrivals that you are having. This is basic resultant of what is the arrival that is happening at your system. Okay, now what can be the possible performance goals for a system which we are representing in such a way. Okay, now when the traffic, so first is your traffic has to be admissible. Okay, otherwise so there will be drops, no, packets will get dropped otherwise. So if your traffic is admissible into your system, then what you have to check, so first is work conservation. Okay, now work conservation is it is a concept. Okay, so I will get to work conservation after I finish all the other parts here. That is, first is that you need to have, you want to have 100% throughput. It's not like you need to have, it is like it is your goal that I would like to have a system where I will try to have 100% of throughput. That is one. Then what you have is that Lijn less than C. That means less than the capacity. Lijn should be less than the capacity C, and for all n. And then you have that your delay is bounded. Okay, so you have bounded delay in your system. And finally, that you might want to consider some other metrics. Okay, some other metrics to basically consider that, okay, how your system is performing. Okay, and finally you have your work conservation. Okay, work conservation will basically, this concept basically talks about that, whatever, I mean, I would want to, no, I will talk about this in the next class with a good, terminology and all that, work conservation, because this is basically that, how good your system is performing. That is the threshold of it. I mean, you need to find out that whether your system is actually a work conserving system or not. That means whether it is, whatever inputs are coming, whether it is actually getting through all of that, whether all of that is going out to the corresponding output port or not. Okay, so this is what conservation is, a concept that we have to understand a little bit more clearly. So I will get to this one when I am looking for the better performance goals, and more metrics, and how we represent such a virtual output queuing system in in this course. Okay, so I will stop the class here today because we do not have further time. So I will stop the class here today. If you have any questions, you can ask. And I do want to discuss something on, we have done 2 modules by now. Okay, so I am thinking that we will have a short quiz now. Otherwise, you will have